Howdy everyone and welcome back. And today we're going to talk about alternating current. Now we've been talking about circuits a little bit. It's always been with direct current, meaning the current's always going in one specific direction looking at any bit of wire, but alternating current's a little different. It's going to be a situation where the current and the voltage actually flip back and forth. It's not always going in the same direction. And maybe our first thought is, why the heck should we care about this? That seems oddly specific. What's the applications of that? Well, it turns out alternating current is really common. In fact, that's how power is delivered to our house. It turns out alternating current's way better at transferring energy at long distances. So we use it in power lines, and it's actually the thing that's coming directly out of your wall. So to get it from alternating current to a direct current circuit, you need an AC/DC or alternating current, direct current adapter. And usually those are the big bricks on the end of a lot of your electronics. But also alternating current is really, well, it's really obvious how you have to create it and to generate it, because we talked about generators a little bit in the last video. If you take a bit of wire and you spin it in a magnetic field, you can create a current, but it's not a direct current, it's an alternating current because it comes from magnetic induction. When you start turning, you increase the magnetic flux, you create a current, and eventually you start decreasing it, so you make then a current the other direction. So it's naturally generated at power plants. It's easier to transfer long distance, and so we use it for a lot of applications. Some electronics like to use it too. So it's actually really common, but usually we start with direct current because it's a little bit easier to keep track. But there'll be some things we'll learn today that are similar to direct current, and there's some things that will be different. I'll try to point out, but it's not like we're going to throw away everything we know, but we're going to still use the same sort of circuit parts like resistors, capacitors, inductors that we've been doing before, but now it's going to be a little different. A lot of things in this subject is doing things that we were can't get my pencil doing things that we were doing before, but maybe changing the context a little bit. I feel like most of the things in these physics classes is something that we can grasp intuitively, and then something that it's really just that, but we just change it a little bit. I mean, that's how we worked with going from linear stuff to things moving in a circle. It's really the same thing, except you just do a slight translation in terms of adding a radius term to a lot of these things, and then changing from acceleration to angular acceleration. So it's a similar thing here. We're still going to have current and voltage, but it may be a max current or max voltage or something called root mean squared. So we'll get that in a moment. So what do we mean by alternating current? We mean that the voltage looking at any given point in a circuit is going to be changing. It's not going to be the same value. It's not going to be static. So at some point there might be no voltage looking at the difference between 2 points, or maybe just consider the voltage of a resistor, but then there's going to be some maximum value, and then it's going to switch direction. So that's essentially all we mean. And we can often write this as being some maximum value times some sinusoid, some sine or cosine. Sines and cosines are the same things except for shifted through a phase. So often maybe just write it as a sine. So we put in a given time. We have some frequency that's being created by a frequency generator. We put in that. So we'll be working a little bit with this equation. So something I do definitely want to talk about is something called root mean squared terms. So we don't have a constant v term like we did before. We often either write it in terms of a maximum term or a root mean squared term. So what do we mean by maximum? We'll take this graph up here, go from the 0 point to here. This is the maximum. So whatever this is going to be called v max. Okay, well, hopefully that makes some sense. It's just the amplitude that's happening. So something we might be interested in is, instead of a maximum value here, maybe we care about an average value. But if we look at here, if we took the average for this, it's going to be just a flat line 0. Every point I have up here, I can find another point that's below. So the average of these things are going to, the sinusoids or triangle waves or whatever kind of waves, always going to be 0. So instead we look at the root mean squared. And what's the root mean square? Well, we square it first. So we take the maximum value, square it. Then we take the mean. That's what we mean by this symbol up here. And then we took the square root, which is this r. So if we're going to draw that out in terms of a graph, so if we have this thing going up here, we want to write the square. If we square something, suddenly it's going to be above the axis all times. Remember, if we square negative numbers, it's always going to be positive. So instead we got rid of all of those negative numbers, and then if we took the average of this, the mean, it's going to be something up here, and then we just take the square root, to reduce down to normal levels. So we don't have to care too much about the math here, but it depends on the shape. For sinusoids, the translation to get from the maximum to the root mean squared is just dividing by square root of 2. And you can do the same thing if you ever had triangle waves or any other types of waves. Same thing for the current. So the root mean squared compared to the maximum, you just have to divide by square root of 2. It's just a slight translation. And something that also carries over is Ohm's law. So you can write the maximums here, or you can write the root mean squares. It just depends what the problem gives you and what you want to, what you're interested in. But there we go. Okay, there's still a lot of things that still work. Another thing that's kind of similar to what we were doing before, but it's a slight translation, is resistance. Now, this Z term is sometimes called impedance, has a few other names, but it's really kind of effective resistance of a circuit. So we're going to be talking about RLC circuits, so circuits with resistors, inductors, the L means inductor because whatever, and then C, capacitor. So it turns out inductors and capacitors have a slight amount of resistance. I like to think about resistance, but sometimes people use impedance or other words, or reactance, because you can sort of get the argument why, since the current is alternating. So imagine, again, I have a capacitor here, and I'm switching the current. So eventually the current's going this way. I pile a bunch of positive charges here. I pile a bunch of negative charges on this side, and then it starts getting uncomfortable. Okay, then I switch the current again, and the capacitor actually really likes that. It likes switching the current really fast, because the problem with capacitors that we learned before is you start piling a bunch of charges for a while, it eventually really just stops working. So it turns out capacitors really like high frequencies. So it turns out the terms of the reactance or impedance or resistance, whatever you want to call it, for a capacitor is going to be 1 over the frequency. So if I have a really high frequency, this term goes really low. So it likes quick changes, as opposed to an inductor. So remember, inductor has the ability, gets affected by magnetic inductance. So when you have quick, and remember, for magnetic inductance, it's quick changes that it doesn't like. It's always trying to return itself to normal. The one loop is creating a magnetic field that affects the other loop, and so if it changes quick, it's going to make currents that oppose that change in the other loops. So this thing doesn't like change. So if I change, I have a lot of frequency. I will have high frequency. I switch back current really fast. It doesn't actually like that. So it turns out its resistance doesn't go as 1 over F, but it goes as F. So the higher frequency, the higher the impedance here. And so you can sort of see it kind of looks like Pythagorean theorem here, except we have two terms: the traditional resistance term from a resistor. This is just that R that we put in here, and this subtraction between an inductor and a capacitor. And it doesn't really matter the order, but we can have situations where these actually cancel each other out, and we call that the resonant frequency when these two things are equal to each other. So if we're asked to get the reactance, or whatever you want to call the word, for a circuit, you just write this whole thing down. Sure, RLC circuits in series are pretty simple to handle, and this is assuming everything is in series. All in line, it gets much more complicated in parallel, but we're likely not going to get to it. Another thing we may care about is the power. So the average power is related to the root mean squared terms, so we need these, not the maximum terms in this case. Just looks like it did before with direct currents, IV, but there's a cosine of a phase angle. So what do we mean by phase angle? Well, we have a voltage and we have a current. So if we draw the current at the same graph, it may actually be the same thing, but off put by a little bit. And we call this difference the phase angle here. And there's a lot of reasons that this happens, but the current is not going to necessarily be aligned. That's what we mean by there being a phase angle. Okay, we can find that phase angle pretty simply taking the arctangent of each side. So we're just taking the arctangent of this stuff, straightforward to get. Okay, so it's almost what's like before, a slight change, something else we'll have to be a little bit careful about, but nothing really dramatically new. And so there's not too much stuff to go over with RLC. This will be a little bit of a shorter video, so we'll only just do 2 quick problems and then go from there. So we have a frequency generator. So this is creating a voltage and it's oscillating it somehow. This one we're told that it's going to do it in a sinusoid, and its function looks like this. It has 98 volts times sine this thing changing, so it's changing as a sinusoid. So we're told also the maximum current going through this, and it just has a capacitor here. There's nothing else going on in this problem. We wouldn't figure out a number of other things. So let's go do that. So we want to find the RMS voltage. So how do we do that? So recall the RMS voltage is related to the maximum by just dividing by a square root of 2. Okay, how do we know the maximum? Well, it's that term that's sitting out in front of the sinusoid. It's the amplitude, it's the maximum value. So we know that. We put that 98 volts, put it in here, divide by square root of 2, 69.3. Okay, next thing. We want to find the frequency. So we're given the function here. So it's 80 pi to pi t, and it's supposed to be a 2 pi f t in here, where this f is the frequency, or if you recall, 2 pi f is really just the angular frequency. We can write that as omega. Maybe we remember learning that a while ago, but if you're just interested. So if we just compare those two things, we know those to be equal. We notice there's a difference of 2, well, there's a pi on each side, there's a t on each side, that doesn't matter. So we have 2f equals 80 hertz. So frequency has to be 40 hertz. Okay. We want to get the RMS current here. Okay, we just divide by a square root of 2. We're told that we have a maximum value of 0.5. Sure, that's fine. Pretty straightforward. And then we want to get the reactance here. So we're just going to use V equals IR. We don't have to go through a big, long, complicated thing. We know the RMS voltage, we know the RMS current. We could just go and divide it out. This is again just V equals IR, but where everything, the V and the I are RMS now. So this should seem pretty straightforward in terms of this is not like we're learning a ton of things. We just have to switch a little bit of what we've been learning, put it in a slightly different context. Okay, last thing. We want to find the capacitance. So we go, and since we know this reactance term, we just solve for it. We are told the number of these things. This thing doesn't actually have any resistance. Doesn't have, there's just 0 here. It doesn't have an inductor. So the only thing that matters here is this chi c. So it's a chi, it's not an x, it's a Greek letter. So the only thing that happens is we get this chi squared and then the square root over it. So it's just chi. That's all that matters. And remember, we learned on the last page, chi is 1 over 2 pi c. So if we want to solve for that, we essentially go and multiply c to the other side, divide z to the other side, and we get a number. And I think what I wrote down here was wrong by a factor of 2, but you get the point of how to go about and solve it. So a lot of just a little problems. There's nothing really hard or huge, no huge revelations here. Just we're switching the context of how we were learning about circuits before. Now the current is switching back and forth. It just changes a little bit. It's not huge. Okay, let's just do one more problem. So here we have another frequency generator creating a voltage back and forth. I mean, this could be from a power plant, this could be from our wall. But we have a resistor, we have an inductor, and we have a capacitor. We're told the values of all these things. We're told the inductance, capacitance, and resistance. And we have a function for the change of voltage over time, or the voltage can be created. At least by here, because it might be more complicated over all three of these things, because they're trying to split the voltage between them, yada yada. Okay, first thing, what is the total impedance or reactance or resistance? I mean, I like to think about it as like just an alternating current version of resistance, because that's how it enters into V equals IR. So we write V equals IR. It's really this Z that exists there now, not R just by itself. It's including the extra impedance that the capacitor and the inductor are adding. Okay, so we write this all out. So we're told the resistance, that's this thing. So we could write out what chi C and chi L are. It doesn't really matter the order because they're getting squared, so the negative sign doesn't matter. We insert that into both equations. We'll insert both of those into our equation. We'll learn what those are on the other page. Okay, and we're told the capacitance, we're told the inductance. We solve for the frequency up here. Again, we were told the function, oh, it's up here. this has to be 2 pi f. This 50 has to be 2 pi f. So we can solve for that. So this is just a calculator problem. We put all these things in, we put all these numbers in. I mean, just be careful with it. We get total reactance of 57.5 ohms. So notice that's just a bit bigger than 40. So it's like Pythagorean theorem. You're just going to have the resistance of the resistor plus some additional term depending on the frequency and capacitance and inductance. So it's a little bit larger than what we have in a direct current situation. Okay, just changing what we mean by a little bit. Okay, then what is the max current? Well, go back to V equals IR, but you know, it's just, let me use a different color. We still have V equals IR, except we can use it for the RMS voltages or we can use it for the max voltages and currents. And now instead of it being just as simple resistance, it's going to be this impedance that we solve for. Again, we're just translating what we have over. We know all those things. We solved for the current. We just got this C. We know the max voltage because they gave it to us in this function. It's 80 volts. Put all those things in. We get a number, 1.39. And so what's going on? Well, it's going from this maximum current. The current's going through everything. It then decreases, goes to 0, then switches direction, goes to that maximum value again, and just keeps going back and forever. That's pretty much all we can really do with alternating current circuits. Of course, electrical engineers can do a lot more. That's not what we're really going after. We just want to get a sort of an idea of what's going on with alternating current circuits. Okay, so I hope you can see, what we're doing is really similar to a direct current, except we're just changing the terms a little bit. We're just translating over. We're adding a few new equations, but otherwise it should be pretty straightforward how to do a lot of these problems. So I'm going to go over an application really quickly, and you imagine you have, one of those old set of speakers where, it's kind of boxy and you can see all the set of speakers in it. You have a big subwoofer down here all the way up to a little tweeter. And so, just with electrical components, how can you actually make sure that the subwoofer is getting all the bass while the tweeter's getting all of the really high-pitched noise? Again, all of these are meant to be better at different frequencies than the other. You need multiple of those little speakers on it to get the full sound. So things are better low end, things are better at top end, and when they combine, that it should be good. So we can actually do that with alternating circuits, alternating current, and using inductors and capacitors. So the idea here we want to get is that capacitors and inductors work good as low and pass filters. So let's go over that. So this won't be a perfect circuit. Imagine it's going back. So I go to this big subwoofer, go to this little tweeter, and I want to add we're not going to be drawing the circuit perfectly. I want to add an electrical component, and I want to think about which electrical component I want to add. So for this subwoofer, I want to get rid of the high frequencies. They're not really helping me. I just want the low frequencies. So what does that? Does an inductor do that? Does a capacitor do that? Well, let's think about inductors for a moment. So inductors don't like quick change. Their resistance term goes as 2 pi f L. So the higher the frequencies, the more it impedes it, doesn't like it. So it actually likes low frequencies. It doesn't like high frequencies. And so imagine the signal that's coming by is a combination of a bunch of frequencies. It's really complicated, all combined together. It's this combination. So what's going to act as a good low pass filter? So what I mean by low pass, it's letting the low frequencies pass through, not necessarily the high ones. So it's going to be an inductor. It likes the low frequencies. It doesn't like the high frequencies. It gets rid of them. It starts creating currents that oppose them. So if we wanted to make this and essentially get rid of the high frequencies, we would put an inductor down here. Now let's think about the tweeter. Tweeters like high frequencies. It likes quick changes, but it doesn't really want the low frequencies. It wants to pass those off to the subwoofer. So what would work well? Well, a capacitor loves switching current really quickly. It loves high frequencies. And so, remember it goes 1 over 2 pi fc. So, because again, if it has low frequencies, it causes charges to build up for a long time. It doesn't like that. It likes quick switches, so it always has charges that can get off, and it has room for them essentially. So I would put a capacitor up here. I would put a capacitor at the top, and that would filter out low frequencies. And so even building just analog components, not necessarily digitally, but just with plain circuits, we can actually create high and low pass filters and make electrical devices, that essentially do their job better. Filtering out a number of frequencies. And you imagine you can build a complicated contraption if you wanted to get one specific frequency through, or block out this and keep that. Combinations of inductors and capacitors could do it for you. So, quick little application. I thought it was interesting. I think that's all I have to today. Good luck whatever you're doing. Thanks for joining me as always. Okay, bye.